Hi guys, I'm not feeling brilliant today, but as usual, I'm hoping that spending some time with you tonight will cheer me up a bit. Can you let me know in the chat if the sound is not okay? Because I'm on my comfy chair, so I'm further away from the microphone. So let me know if there's anything going weird, like you can't see or can't hear. And hope. Oh wait, how's that? Can you? Yeah, I think it's okay. You have to let me know if you can't see, because like this is confusing, all the stuff on the screen. Okay, so what are we going to do today? We are going to continue with our mechanics. I think in all we're going to do about 6 sessions on mechanics. We're going to do one today on pulleys, and then we're going to do another one this week on all of the F=ma problems that are not pulleys. And then we'll have one on variable acceleration. I think we can cover it in one. We'll have one on, now constant acceleration, the SUVAT, I'm going to pull it out a little bit because a lot of people have trouble with the vertical SUVAT. So vertical flight, a ball flying through the air, being thrown up in the air or being dropped off a building or something like that. So I think we're going to do vertical and horizontal separately for SUVAT, even though it's still all SUVAT, and then we'll do a completely separate one for VT graphs. Not that they're different, but the techniques you use are different. So I think that's going to be the best way. So that's 6 sessions, but we'll come back to anything if you need more time on it. Yesterday we talked through this structure and what's in each bit. Okay, extending from yesterday, the pure. So our central spine is the differentiation, the integration and the trigonometry that we need to practice a lot. So we're going to practice a bit of that, and then we're going to conquer pulleys. Reminder of the Chili rating system that you can use to, whenever you're learning a new pure topic, to think, am I meant to be finding this difficult? Am I meant to be finding this confusing, or should this be okay? Anything on the left hand side should be alright. If not, maybe you haven't learned it in a way that's made it click for you, because really it should just click, and you don't even need to particularly think with those topics, you just do a routine. The ones on the right, they take a long time to get good at, and they take lots and lots of practice, so it is super duper important to introduce them early if you're going to get good at them and confident with them. And obviously the number of marks tells you the relative importance in terms of what you're going to be rewarded for your confidence with that particular topic. Okay, chain rule practice. So there's 10 derivatives, and you need to look at the expression that you need to differentiate and see, what is that outer function? What am I basically being asked to differentiate here? Albeit it might have something else inside it. So the first one, I put a little 3 on the front, just to remind you from yesterday that anybody sitting at the front watching is totally fine. They can just sit at the front and watch. We don't need to worry about it. Same with this 4 here. Now the first one I think is the most obvious. The function that we're differentiating is learn, which is down here. And then the function that has gone inside learn, the thing that isn't an x, the thing that if the world was easy would just be an x, is 2x squared plus 1. So that's the bit that the chain rule will help us deal with. Next one, the function that we're looking at is e to the, and the derivative of e to the is e to the, but it's not e to the x, it's e to the blah 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 blah. So that's the stuff that the chain rule will help us deal with. Third one is difficult to spot in its current form, so I'm going to rewrite this as sec x to the power of 6, which obviously does mean the exact same thing, but in that form we can see that what we're looking at is something to a power, which is the 10th derivative down here, the one you learned in the first year. Pull the number down and take one off. Okay, from here I'm gonna zip and do it quietly, so you can watch or you can have a go and then look at the screen. You can pause it and then have a look, and just give me a shout in the chat if there's anything in here that you think, well, I didn't get that, or I'm not sure why you did that. Okay. Okay, there's the first one. If I wanted to tidy this up, I'd put all of that 12x on the top. Next one. Okay, derivative of e to the is e to the. Now I need to differentiate 3 sine. I've just realised I didn't do a very good job at shutting up, did I? I'm doing it out loud. Never mind. I gave you time, I think, enough to have a little play yourself. So the derivative of e to the is e to the, but now I need to multiply by the derivative of this guy that was not just an x, it's 3 sine 2x. The 3 is not important, the 3 is just sitting at the front here. I'm differentiating 3 sine 2x. Derivative of sine, first one on our list, is cos. Now it wasn't an x, it was a 2x. So it's not exactly what's here. Derivative of sine x is cos x, but the chain rule says that if we have the derivative of sine 2x, it will just be cos 2x, but then we must multiply by the derivative of the thing that was not an x. The thing that was not an x in this case is 2x. Derivative of 2x is 2. So if I did want to tidy that all up, I'd put the 2 and the 3 multiplied together at the front with the cos 2x, and then the exponential. Okay, last but not least. So the 4 at the front, just let the 4 sit at the front. The 4 is not doing any harm. Okay, we realised that what we're looking at here is actually the 10th derivative, something to the 6. So I'm going to pull the 6 down and change it to a 5. And then I'm going to multiply by the derivative of the thing that wasn't an x, and in this case, because the function I'm differentiating is to the 6, the thing that was to the 6, the thing that isn't an x, is sec x. So I'm going to multiply by the derivative of sec x, which is sec x tan x. So this one is a bit funny. When we simplify it, look what happens. We get the 6 times 4, obviously that's just the number. But now, actually, I get sec to the 6 back, and a tan. Because the power went down, oh, you can't see it, hang on. The power went down, but then, because the derivative of sec x is sec x tan x, another sec x appeared, so then the power went back up to 6. Okay, there's our chain rule practice for today. Let's move on to our integration practice for today. Now, when you're integrating, really you're not integrating. You are working out what was differentiated to create this function. What was it that got differentiated to create this function? Now, these 3 should be a little bit familiar to you, because essentially the things we just differentiated are the things I now put in integrals. Not the things we differentiated, sorry, the derivatives. So the puzzle is, what did I differentiate? What was it that I started with, and then I did differentiation, I used the chain rule, and I got this. So the better you are at the chain rule, the easier this basic integration gets, but it's still really difficult. It's still 3 chilies. It takes such a long time to get good at, but we're going to do some every day, a little bit like this. Okay, the first one. Well, the only thing that we differentiate to get a fraction is ln, but it's only ln of the bottom if the derivative of the bottom is on the top. That's what the ideal scenario is, a integral of a fraction, and you look at the fraction and you differentiate the bottom of the fraction and you see that derivative on the top. That is showing you that the chain rule got used for ln. So this one, the derivative of 2x squared add 1 isn't 6x, I admit. The derivative of 2x squared add 1 is 4x, but that's okay, because killing numbers is totally fine in this context. We know exactly how to kill off any numbers that pop out. So this has come from, I'm going to just let the 6 sit at the front. I'm just not even going to think about the 6. The derivative of learn is 1 over. So if I put that learn there and then I think about differentiation, so not integrating, now my brain is going in this direction and I'm differentiating learn of 2x squared plus 1 to see what I get. When I differentiate learn of 2x squared plus 1, I get 1 over 2x squared plus 1, which is great, but then I have to multiply by the derivative of the thing that wasn't just an x. Now this here is not just an x, it's 2x squared add 1. So the derivative that I would have to multiply by when I'm using the chain rule is 4x. Now if you look, the x is there. I want the x. The x is perfect. If the x wasn't there, it wouldn't be learn, because it wouldn't work. If I differentiated it, it wouldn't equal the thing that it needs to equal. So the x is totally fine. The x is brilliant. It's the 4 that's the problem. So because of this 4 that I want to get rid of, I'm going to put a quarter at the front. And that quarter, when you think about the differentiation process, it will get killed off. The quarter will kill the 4 that comes out because of the chain rule, and then this works. That 6 is that 6. The derivative of learn is 1 over. But then I multiply by the derivative of the thing that wasn't an x, which is 2x squared add 1. That derivative is 4x. The 4 will get killed by this quarter, and then the x sits on the top, which is where I wanted it. So if you were simplifying this, the only thing we'd have to deal with is the 6 over 4. Okay, next one. The only thing that we can differentiate and get e to the is e to the. Now in this case, I can see that there's e to the something complicated. Just like in the fraction case, there was 1 over something complicated. But see how the derivative is sitting right there. The derivative of 3 sine 2x is basically cos 2x. There's a number, but we can kill numbers, so not a problem. So I can see that derivative sitting there, which means I know that the chain rule got used, which means I know what got differentiated. It was this. That's basically the answer. Now I need to do the differentiation to actually think this through. What happens if I differentiate e to the 3 sine 2x? I would get e to the 3 sine 2x. Perfect. And then I would multiply by the derivative of 3 sine 2x. Now the derivative of 3 sine 2x requires the chain rule. So now, obviously, when you've got a whole sheet of A4, you've got room to go do all this stuff. I'm doing it in my head. The derivative of 3 sine 2x is 3 cos 2x times 2. It's 6 cos 2x. Now I want the 2x. That's perfect. The cos 2x is right there. And I wanted it. And I saw it. And that's how I knew what the integral would be, what thing got differentiated. But I do not want the 6. So in order to make that 6 disappear, I'm just going to put a little 6th at the front, and we're done. The answer is 1/6 e to the 3 sine 2x plus c. Okay, the next one. Now, if you hadn't just differentiated something and got something looking very much like this, then this would be a hard integral, because you're looking at it and there's nothing that differentiates to this, nothing. If you differentiate sine or cos or tan or sec or cosec or cot, you don't get that. But if you think of it just slightly differently, if you think of it like this, now it becomes a very, very easy integral. Now I can see the derivative of the thing that wasn't an x. I can see that the chain rule got used. I can see that what I must have differentiated must have been sec, but to a slightly higher power. And I'm just going to keep this notation, I think it helps. There's no reason not to, it's not wrong. So if you differentiate sec to the 6, what happens? Thinking it through, so going in this direction, thinking about differentiation to see whether or not the thing that I think is the answer is the answer. So the 6 would come down and change to a 5, and then I would multiply by the derivative of sec x. Now the only part of that I don't want is the 6. 6 comes down, I don't want a 6 at the front, there's no 6 at the front there, don't want it, so I'm going to put a 6 here to kill the 6 that comes down. 6 comes down, changes to a 5, that gives us sec x to the 5. Then we multiply by the derivative of the thing that wasn't an x. The thing that wasn't an x, it wasn't x to the 6, it was sec x to the 6. So we're going to multiply by the derivative of sec x, which is sec x tan x, and that makes that the perfect derivative, which means I have the perfect integral. I have the answer correct. As soon as I've found the thing that got differentiated, I've done it. I've got the integral. Okay, so we've done our chain rule practice for today, we've done our integration practice for today. Here is our trig practice for today. Again, all of these topics, they take a long time to get good at. We have to come back, come back, come back. So don't be annoyed with yourself if every time that you do this you feel like, well, I don't feel like I've got any better. That's just what maths is like. It feels like you're not getting better the whole time, and then suddenly, not even suddenly, but at some point you look back and you think, oh, I'm so much better now than I was. But the whole time you were doing it, it will have felt horrible. Just realised you can't see the right hand side of the proof, so I'll just move that down a bit. So yeah, maths is psychologically quite difficult to do. You always feel like you're not getting anywhere. So what's the definition of sec and cosec and cot? Look at that third letter and that will remind you. It's the reciprocal of cos and the reciprocal of sine and the reciprocal of tan. Okay, thing to point out, it's not that sec and cosec and cot are bad and sine and cos and tan are good. It's not that if we get an equation or a proof and it's got sec or cosec or cot in it, then we must quickly get rid of it and get everything in terms of sine and cos and tan, because sine and cos and tan are good and sec and cosec and cot are not good. If that was true, why would we introduce 3 new functions whose only purpose was to be annoying and we have to somehow get rid of them? That would be ridiculous. The reason that we introduce sec and cosec and cot is that they actually, once you're comfortable with them, simplify our lives. So it will feel at the beginning that every time we see these reciprocal trig functions, we're just swapping them back to being 1 over sine and 1 over cos and 1 over tan, but that's really not the case. With this first one, we have a quite common setup, which you might start to recognise. It's 2 separate terms on one side of the proof, and then 1 term on the other side of the proof. So on the left hand side, somehow these 2 separate things have been merged together, pulled together, stuck together into 1 term. Very, very common to see this in trig proofs, this structure, and it's almost always the best thing to do is to write the left hand side as fractions, and then we can add the fractions. So cot I'm going to write as 1 over tan, and tan I'm going to write as tan over 1. So the advantage of doing it like that is that now I have fractions, and I can now use my GCSE knowledge about how to add fractions. I'm going to multiply the top and the bottom of this one by tan to make the denominators the same. So this is the left hand side that I started with here. Multiply the top and bottom by tan. Then I've got a common denominator, which is great. And also, I've created 1 term. That's the main thing. I had 2 terms, and I've squished them, and then there'll be 1 term. So this is going to be 1 over tan theta plus tan squared theta over tan theta. Now I've got that common denominator, which is brilliant, so I can add the tops and leave the bottom the same. Now I've got one thing. See, I squished them together. So that's good. Now 1 plus tan squared, there's an identity for that. It's like, we'll come back to the Pythagorean identities another lesson, but this one is very similar to sine squared plus cos squared is 1. That formula, sine squared x plus cos squared x is 1, has two cousins in the world of reciprocal trig. And the one that I need today is this one, tan squared x plus 1 is sec squared x. This hexagon is really nice. See how the cos and the sec are opposite each other? They're the reciprocals of each other. And opposite the sine is going to be cosec, and opposite the tan is going to be cot. And that arrow reminds you of how the formula goes together. Sine squared plus cos squared is 1. Tan squared plus 1 is sec squared. Tan squared plus 1 is sec squared. So on the top here, I'm going to make it even simpler and write it like that. Now it's not quite how we want it, but it's definitely getting there. Fractions is often the worst part of dealing with proof in trig, because we've got these reciprocal trig functions and they create fractions, and working with fractions is not really most people's favourite thing to do. So watch what I'm going to do with these guys. I'm going to separate them. I'm going to slide that sec squared over to the right and the 1 over tan to the left. Like that. So I've got 1 over tan theta multiplied by sec squared theta. Let's move you out the way a minute. Okay, 1 over tan, I can write it as cot theta, or cot x in this case, because cot and tan are the reciprocals of each other, so I can change that now to cot, but I don't want to. And the reason that I don't want to is because I'm trying to reach cosec times sec. That's what I'm trying to get to. And cot is not one of those two. So if I change 1 over tan x to cot x, it won't be wrong. It just might take me down a path that's a little bit longer to get where I want to get, which is totally fine. At the beginning when you're learning this, going down the wrong route and wandering around for a while and then getting there is absolutely perfect. That's how you learn. But I'm not going to change it to that. I'm actually going to change it to cos over sine. And I'm going to change the sec squared to 1 over cos squared. And that is not because sine and cos and tan, or sine and cos, it's not because sine and cos are better. The right hand side of the proof is cosec and sec, so I need reciprocal trig functions, but it's going to help me to see what cancels with what and how I can write these two things that are times together as cosec sec. Okay, so I can divide the top and the bottom here by cos, which means on the top I get 1 over sine now, and on the bottom 1 over cos. That step I think is the hardest step of this whole proof, is the GCSE fractions-y bit of it. And I'm now done. 1 over sine theta is cosec theta, 1 over cos theta is sec theta. And the proof is done. What did I have to know? Not much. I had to know the definition of sine and cos and tan. No, no I didn't. I had to know the definition of sec and cosec and cot. And I had to know that Pythagorean identity, tan squared x plus 1 is sec squared x. But those bits of knowledge, they wouldn't really on their own have helped me. It's much more about the experience and the confidence with the fractions. That's what I really used. That's what really got me from the left hand side to the right hand side. Okay, let's have a look at our equation here. I'm going to talk you through it like I did yesterday, the way that I like, which is not the graph method and not the quadrant method. But first, I have to get it to the point where I can solve an equation using the calculator. I have to get it to say sine of something is, or cos of something is, or tan of something is. Okay, I have cot squared and I have tan. Cot is 1 over tan, tan is 1 over cot. I could do either here. I'll go with changing the tan, I think. No, I'll go with changing the cot. It doesn't matter. It's going to work either way. But the reason I was thinking I'd change tan to 1 over cot is to reinforce this idea that cot is not worse than tan. I'm going to change this to 1 over tan. I think that's probably what most of you would prefer. Okay. Now I do not like that fraction. It's easier not to have a fraction. So I'm going to go along and I'm going to multiply everything by tan squared. So I'm going to multiply the first term by tan squared. I'm going to multiply the second term by tan squared, and I'm going to multiply the right hand side by tan squared. That's looking much nicer. Not that there's anything wrong with fractions, it's just looking tidier, cleaner, easier to deal with. Okay, let's put the 8 tan cubed on the other side and divide both sides by 8. And then let's cube root both sides. Okay, we have reached AS. We have reached the point where we're going to solve a trig equation on a given interval. We've reached the point where I'm going to try and convince you that this method is better than the graph method or the quadrant method. What did I need to know? I needed to know that cot means 1 over tan. That's about it, isn't it? Everything else after that point is AS or GCSE manipulation. It's a standard technique, what I did there, to not really like having a fraction in my equation and to multiply through, like sweep through, cleaning out the bottom of that fraction to make it look nicer. And then from there, simple rearranging. So how are we going to solve this? First of all, I'm going to just get the calculator and do shift tan. Easy peasy. I'm in degrees, which is perfect. Shift tan of a half is 26.56. Okay. Easy. From the calculator. Second solution. There's only 2 solutions. There's always 2 solutions. And this is the only bit where it matters that this was tan rather than sine or cos. Because to get the second solution for tan, I do 180 plus the first solution. And that's the only time it matters that it was tan. Everything else is going to be identical for sine or cos or tan. So I'm going to add 180 to that one to get the second solution. Okay, next I'm going to turn my 2 solutions into 6 solutions by taking each one, taking 360 off it and adding 360 onto it. And I am not looking at the range. I would do this regardless. I'm not doing this because of anything to do with the question, it's just what I would do. This calculator is not backlit and it is so hard to read. I think that's right. Now I'm going to take the 26.56 and add on 360. and take off 360. If I'm copying the calculator wrong, then please let me know, and apologies. It's just really hard to read these guys in the not brilliant light. Why haven't I not got better light? I'll put a brighter bulb in. Okay, minus 360. Okay, so I took my first solution from the calculator, turned it into the second solution, then I had 2 solutions, I've turned that into 6 solutions, and now I'll have a quick little look to see what it is that I found. It's 2 theta, because the thing in the brackets is 2 theta. So all of these guys are 2 theta. So to get theta, I need to halve them all. Okay, bear with. And I'm going to write them in the same order, in the same position, so I know where they all came from. I cannot see what number that is. 76. 208. Okay, I have my 6 answers. Now, and only now, would I look at the range. 180 to 360 apparently. Now I know you might be thinking, well, that was silly of you. Why didn't you just look at the range before and then a load of that? You wouldn't have had to do. That's true, but overall, the net amount of thinking required to do that is greater than the net amount of thinking required to do it the way that I'm doing it. And what I want is for as much of the exam to just be an algorithmic process that I can just do without thinking, and that's going to leave me with all of my little thoughts to use on the difficult questions and the things that require me to think. I don't want to have to think while I'm doing this. I want to just be able to just get the answers. So having a look now at my 6 and having a look at the 180/360 rule, I don't want those two. I want that. I want bigger than 180. Don't want, and I want smaller than 360, do want. So I found 2, but there might be some more. So I'm going to pop back to my other list. And because it's so easy to add more to my other list, I just move these guys up a bit. All I need to do is put another 360 on. Simple. And because I've laid it out really clearly, I know what to add the 360 to. So 396.56 add 360 is this number, and I'm writing it down because the examiner likes to see what I've done and will give me marks for these numbers. Divided by 2. It's too big. Only just though. In which case, this next one's going to be too big, isn't it? 566 plus 360. This is going to be massive. 926 point something. And then if you divide that by 2, it's going to be 400 and it's going to be too big. So I now am absolutely confident that I found the solutions, and the only 2 solutions between 180 and 360 to solve this particular problem. Okay, we've done our, let's just go back, check what we've done. We have done our chain rule practice, we've done our integration practice, and we've done our trig practice. Now what we need to do while we're strengthening that spine, we need to start peppering in all these other guys, all these other topics. But today's topic is F equals MA, and we're going to look at pulleys, and we're going to look specifically just at first year ones, because we're tying up and consolidating and boosting that first year mechanics so that it's such a strong basis for the second year mechanics that the second year mechanics will be super duper easy. Okay, where do they start? Let's see. Here. Now in the first year, there are two types of pulley problems. The ones that look like this, and the ones that look like this. Dunk, dunk. And that's it. And they ask them about 50-50 whether or not you're going to get a up and down, a pulley hanging over something or a pulley over a right angle. It's about 50-50. And in the second year there's more scenarios, because in the second year you learn about slopes, but that's going to be okay. It's going to be exactly the same steps. Another thing I just want to point out here is that this particular one, there's no distances anywhere drawn on. They might tell us in the question, they might tell us later, they might say, oh, P drops 1.2 meters before it hits the ground, or Q does, or whatever, but they're not drawn on the diagram. Same here. It's just the mass, not any distances that they're going to travel. Now what that tells you is that we may not be doing a SUVAT at the end of the question. If they tell us a distance or a time, then we will be doing a SUVAT at the end of the question. But see, this one, I can already tell you that we are going to be using a SUVAT because there's a little distance there. Same with the next one. Some distances between the ground and the pulley. Now F equals MA is about forces and mass and acceleration. It is nothing to do with displacement or distance or velocity or time. None of those things. F equals MA is forces and linking those forces with the mass and the acceleration. So those distances that have been drawn on there, they tell me that I am going to be using SUVAT as well as using F equals MA. It's very common, as you can see. There was a couple where we weren't using it, but most of them were using it. No distances drawn on there, although it could be in the question that they mention time or distance and we need it, but it's not drawn on the diagram. That one is. That distance there tells us that we're going to be using SUVAT after our F equals MA. Same here. Distance travelled to hit the ground. It's very, very common. Same thing here. That distance. And this one, no. No distance is there. But it might come up in part C. It might tell us some time or some distance or some speed. And then we know that we're moving on to SUVAT because F equals MA doesn't include any of those things. It's just force and mass and acceleration. So how do all these guys work? What you are going to do is a force diagram for each of the two particles. Then we're going to do F equals MA for each of the two particles. And then we're going to do simultaneous equations. And that will allow us to solve the problem. Regardless of what it says underneath there, that will always allow us to solve the pulley problem. So let's start with the diagrams. What forces do we have? We have weight always. Weight's going to go straight down. Weight is mass times gravity, mg. Might not be m though, because if the mass, is 2m, then mass times gravity would be 2mg. So weight, mass, times gravity on the planet that we are currently on. This scenario being Earth. That's force number 1. Force number 2 and number 3 I'm not going to mention here because they only occur when we've got a surface in contact with our particle. So we've got our particle P or Q and it's on a table or on a slope. Then we're going to have a normal reaction and we're going to have friction. But these dangly pulley ones, nothing's sitting on a surface. So those two, the reaction and the friction, we don't need to worry about. 4 is the tension in the string, which obviously we do have, and it goes in the direction of the string. It's almost like you're drawing the string. but you're drawing a force diagram. And then the fifth one is like an engine or somebody pushing something or some other thing, or like resistance that they tell you about, just something additional that they've added in to the problem. That's not going to be relevant in these ones either. It's just dangly things over a pulley. So P looks like this: weight, tension, and Q looks like this: weight, tension. Why is it the same tension? It's the same T because the pulley is smooth, and the pulley will always be smooth. And if the pulley isn't smooth, then what they'll say is, what did you assume? And then you say, I assumed the pulley was smooth, because you used the same letter T. You didn't use different letters T. Here it says smooth pulley. That's why the T and the T are the same. So that's job number 1, force diagram. P, weight, tension. Q, weight, tension. Why is it the same tension? Because the pulley is smooth. Let's see if I can find that information. Here it's fixed pulley. The string passes over a fixed pulley. The pulley is modelled as being, there we go, smooth. That's why the T's are the same. These don't get named, so I'm going to call them A and B. A, weight, tension. Weight, tension. I think you get the idea. Let's move on to the ones that are on a corner. I'll show you, that gets a little bit more complicated, but not really. Okay, this one, we have the weight, and we have a normal reaction and friction. So because this is on a surface like this, we've now got these extra forces, number 2 and number 3, the normal reaction and the friction, unless it's a smooth surface, in which case no friction, but still normal reaction. So the van, we have to think about these extra forces, number 2, normal reaction, number 3, friction. So let's see if it's a smooth surface or whether it's a rough surface. It's a smooth pulley, which is good. It means T will equal T. But I'm looking for whether or not the van is on a smooth... Oh, it's not, look. A constant resistance force of magnitude 780 newtons acts on the van. So maybe that's a combination of air resistance, friction with the floor, those kind of things. 780. Okay, let's 1, 2, 3, 4, 5. I've done the weight. I've done the reaction and the friction. Number 4 is the tension in any string. Yep, we've also got that because the string or the cable is coming out of the back of the van. And you draw the tension force as if you're drawing the string. We're not, but... And then number 5 is an engine or a push or something like that. And if you see, it says here, the van's engine produces a constant driving force. So we do have another force there. So look how much more complicated that force diagram is than the dangly pulley things. Much more complicated. But it's still the 5. Still just thought through the 5, went through the 5, found the missing information and used it to draw the force diagram. Now we do the force diagram for the crate. So we've got the weight. We've used the fact that the mass is 1,300 kilograms. The crate is 300 kilograms. And we've got the tension in the string, and that's it. So yeah, these are harder to draw, but they're not always going to be that complicated. Look at this one. Here's A. We've got the weight. We've got number 2 force, normal reaction. Number 3 force is going to be frictiony resistance which will be parallel to the surface. So it's either going to be going that way or that way, but not if the table thing is smooth. So I'm just going to look through it. Oh, it's a rough horizontal table, rough. So there is going to be some friction. The B ball, the one hanging, that's the one that's going to go down. So A is going to go right, which means that the friction, the resistance force, is going to try to stop it. It's going to go in the opposite direction, left. Let's see how big that friction is, that resistance force. String passes over a pulley, which is fixed. The other end, still haven't told me that it's a smooth pulley, by the way. The system is released from rest. The string is taut. I'm looking for resistance. The resistance to motion from the rough table is 12.7 newtons. There we go. So weight done, normal reaction done, friction, resistance, force done. Next, tension in the string. Yes, it's as if we're drawing the string, but we're not. And then an engine or a push or any other forces that are mentioned. There's no other forces mentioned. B, weight and tension in string. Why is it the same tension? Because it's a smooth pulley. Let me find it. It needs to be a smooth pulley, otherwise I can't let those T's be the same. Resistance to motion, rough table, the balls are modelled as particles, the string is light and inextensible, the pulley is small and smooth. T is T. Okay, so that is step one. Draw the two force diagrams. Step two. And it all pulley questions. First year, second year, same 3 steps. 1, force diagrams. 2, F equals MAs. Now in order to do F equals MA, I need to know which way these particles are accelerating. Who's accelerating up, who's accelerating down. So in this case, it's always going to tell you, and it will say, find the tension in the string, immediate particles are released, and 5 kilograms, this one's going to go down, and this one's going to go up. The heavier one is going to go down. So just going to add that to my diagram just to make sure that I get the right positive and negative. And my pencil was doing this earlier as well. It's a bit annoying. Pencil charged. I think it's the app. See, I'm drawing and drawing and it's not doing anything. Can anyone recommend to me a good app that I can use to share my iPad? Because every single one that I've tried, it should be really simple, but every single one that I've tried does this kind of thing, which is really frustrating. Obviously, because like the whole point is that I want to write. The only thing I can think to do is close it and open it again. The project. Okay, fingers crossed. Yay. Okay, that one's accelerating down, that one is accelerating up. Why does this matter? It doesn't really, but I need to have in my own mind whether or not I'm taking uppy things is positive or downy things is positive. And when I write F equals MA, I don't want a negative acceleration. It just is a pain. Because if the acceleration is negative, it's accelerating in the opposite direction, and it just means I have to sub in minus A instead of A. Oh, why is it the same A? It's the same T because the pulley's smooth. Why is it the same A? It's because the string is inextensible. Where is it? Inextensible string, A is A. Smooth pulley, T is T. Getting those the right way round is often a mark because they will often ask about it. Okay, so it's the same A, it's the same T, totally fine. I'm using F equals MA. I'm going to take all of the down bits here as positive. Oops. So I'm going to do F equals ma, and anything going down will be positive, anything going up will be negative. So the forces acting will be 5g, which is positive, and t, which is negative. And these equal the mass times the acceleration. And I think the highlighted thing helps you to see what forces need to go into the F of your F equals ma. This one, I'm going to take up is positive because it's accelerating up, which means that my A can go in as a positive number, which means I don't have to worry about putting a minus sign in with the A on the right hand side. I just want the right hand side to be the mass times the acceleration, and I want that to be a positive number. That's why I'm taking up is positive. Okay, so the forces, I can see I've got T positive, 3g negative equals the mass times the acceleration. Equation 1, equation 2. Diagram, F equals ma, then simultaneous equations. It will always work. Okay. F equals ma. Which one's going up? Which one's going to be the positive acceleration? Which direction? Let's see. So one of them has got a mass of 3m, the other one's got a mass of 4m. So this guy is going to go down and this guy is going to go up. So I'm going to take all of the down bits as positive for the F equals ma and all of the up bits as negative for the F equals ma. Down minus up equals mass times acceleration. Equation 1. Next one, up minus down equals the mass times the acceleration. Equation 2. Why were those accelerations the same? Because it's an inextensible string. Let me find that, just be sure. Yep, there we go, inextensible string. So A equals A. Smooth pulley, T equals T. Diagram, F equals ma, simultaneous equations. I'll do one more of these and then we'll have a look at that more complicated version. So who's going up and who's going down? This one's 1.8, this one's 1.2, so the 1.8 is going down, so this will be positive. And any forces that way will be positive. Okay. You're positive, you're negative, equals mass times acceleration. Equation 1. You're positive, you're negative, equals mass times acceleration. Equation 2. Diagram, F equals ma, simultaneous equations. Okay, let's look at the more complicated scenario here. We've done our diagrams. The crate is accelerating up. The car is accelerating right. There is no acceleration for the car up and down. In this direction, as in underneath that pink highlighter, there is no acceleration. There's no positive, there's no negative, there's no acceleration. A is 0, so all those forces balance. So I could do up is positive and have R minus 1300G is 0, or I could take down as positive and have 1300G minus R is 0, or I could just say all the ups equal all the downs, because the acceleration is 0, so the forces are balanced, the resultant force is 0. Now, for this one, I'm going to get 3 F equal MAs, not 2, 3. I'm going to get the one for the crate. F equals MA. I am going to get the one for car. F, anything going backwards is negative, equals MA. Why is it the same A? Because it's an inextensible pulley, cable. It's an inextensible string. It's an inextensible cable. Let me see. Let me find it. There it is. Inextensible. A equals A. Pulley, smooth. T equals T. Good. Now there's another one. There's 3 here. F equals MA, F equals MA, and F equals MA. Albeit with A is 0, this one is going to be A is 0. Therefore, all the ups equal all the downs. I'm going to do it that way. R equals 1300G. Now, step 3, simultaneous equations, I might not need to use all of them immediately, but that's not the point. It's the same as I was saying about that trig method. What I want is for the vast majority of the questions in the exam for me to not have to think. And pulley questions are like that. We don't have to think. We know. I haven't read any of these questions, but I know I'm doing the things that will get me the marks. Force diagram, F equals MA, F equals MA, F equals MA, simultaneous equations. Now, what's the most difficult part of that? It is the simultaneous equations. Well, the force diagrams take maybe a little time to get more confident with than used to, but the simultaneous equations is the hard bit. What you're going to be doing is taking one of them, one of your F equal MAs, rearranging it to say T equals or A equals, and subbing it in the other one, and then solving. Same thing here. Make one of them say T equals or A equals, stick it inside the other one, and then solve for A or for T, whatever it is that they want you to find, or maybe even for M sometimes. Same thing here. Make one of them say T equals, stick it in the other one, rearrange, simultaneous equations. Now when you get onto ones like this, you've got 3 equations that you can use. They might not be interested in R at all. In which case, this guy just sits there. He doesn't get used, but he still sits there. And what happens is that in the second year, when these get harder, when these are slopes, by following these steps, by knowing that you're always going to be doing the same thing, you will get marks. You will get like 2 marks for each of your F equal MAs. So you will be getting a bunch of marks, even if that's as far as you get is force diagram, F equals MA, F equals MA, F equals MA. But then, regardless of what these say, it's going to be simultaneous equations. It's going to be taking one of them, rearranging it, sticking it inside the other one, and solving that. So, we have covered pulleys. And actually, not only have we covered pulleys in the first year setting, but there is nothing different in the second year setting at all. The only difference in the second year is that we have things on slopes. So the force diagram is a little bit more complicated, and I will go over that with you before the year is out. But pulleys, you are now free to go practice. Ignore the part C's. As soon as they introduce speed, or more likely distance and time, then we're veering away from that F equals MA, and we're going to be doing a SUVAT or 2 SUVATs. So don't worry about that bit for now. Just focus on this one skill that we've learned today, which is if you have a pulley question, it is diagram, diagram, F equals MA, F equals MA, F equals MA, simultaneous equations. Okay, can you hear the lovely rain? I have a Velux window here, and I love sitting and listening to the rain. Okay, I shall let you go because obviously my voice and chest is starting to really hurt now, but I will see you tomorrow and we'll do some more maths. Take care.